Hello and welcome. So this is something different. This is a second pre-lecture video for the first half of Chapter 9. We'll also be hitting on some of the topics from Chapter 8 that we're hanging over from our previous lecture. These are actually the slides I have planned for tomorrow in lecture. I will probably be throwing these examples more to you guys to do. We won't have very many top hat questions in class tomorrow, so instead I think we'll have the class working in groups on solving structures just like these ones here. So if you understand these problems, then hopefully you can help the class understand them better tomorrow and learn a little bit more about these topics through being able to explain them to others. And then also maybe just having some questions or ideas that you can get straightened out through class. Now what I wanted to do with these two examples here is kind of zone in on the three general ideas that we have. Whoa, why is that so big? I want to zone in on the three basic ideas that we have for determining Lewis structures and kind of compare and contrast when to apply each of these different ideas. Okay, one is that you can use like Lewis dots. So you can have your hydrogens on the outside. Now we know they should be on the outside. Hydrogens only forming one bond. Oxygen here. In fact, oxygen didn't end up. Oops. Can't write in a straight line today. Okay, so here we might connect our single bonds, and we end up with lone pairs on oxygens, zero formal charges the whole way around the molecule. So like Lewis dots kind of work pretty well for something like hydrogen peroxide. Now another approach could be, so that's like method one is like Lewis dots. Method two could be, okay, can we just use the idea that oxygen should have two bonds each, and hydrogen should have one bond each, and oxygen should have two lone pairs. Like, so nitrogen should have, three bonds, one lone pair. Carbon should have four bonds. Halogens should have one bond and three lone pairs. Not in all compounds, but in cases where they're going to end up with a zero formal charge, in order for these compounds to have an octet and a zero formal charge, those are the bonding arrangements that they should have. Now, a third approach would be locate the central atom, connect the non-central atoms to those. So we end up with a base structure like this, count up our electrons. In fact, another check for both of structures 1 and 2, or methods 1 and 2, would be to count up our valence electrons, 1 times 2 for the hydrogens, plus 6 for each of the 6 for each of the oxygens. So 6 times 2 is 12, plus 2, 14 electrons should be shown in our structure. So we have 2, 4, 6, 8, 10, 12, 14. And same thing for 2. And then likewise for structure 3, we would look and say we have 2, 4, 6 electrons given. So we need 8 electrons. So 2 pairs of electrons on each of the O's. So you could get to the Lewis structure of hydrogen peroxide. Any one of these three ways gets us to the exact same structure. So we have three ideas that we can apply. Now, usually when you have one central atom, say you have a weird molecule like BRF5. Maybe you've never seen a structure like this before. So a molecule like this one, I'm thinking, okay, I'm just going to count the electrons, and then I'm going to distribute through attaching single bonds to the central atom, and then kind of going from there to see if I have leftover electrons to put on the central atom, and then thinking about formal charge to think if I need double bonds, maybe thinking about the octet rule, if I want to expand the octet, maybe looking at the specific question to see whether or not we should consider expanding the octet. So I think for something like BRF5, I'm going method 3. Now, NCO minus is kind of a weird one, where methods 1 and 2 are going to struggle. And let me show why that's the case. So nitrogen, we said, should have 3 bonds and a lone pair. And that, not on all compounds, but in order for it to have the satisfaction of the octet rule and a zero formal charge, that would be the case. So then carbon should have 4 bonds, no lone pairs. And so then carbon would want to have a single bond to something like oxygen. Now, a problem here would be that oxygen generally wants to have 2 bonds. So how are we going to get 2 bonds here? Like if I put a second bond in, then I have 5 bonds to carbon, and I cannot have 5 bonds to carbon. And so then maybe I say, okay, well, I'll go with this structure here. Minus formal charge on oxygen. We've seen that in some cases before. 0 formal charges on C and N, so that's not particularly bad. So we may arrive at this Lewis structure and then say, okay, that's the right answer. And it may be, but we may revert back to method 3. So if we go back to method 3 for our Lewis structure, then what we might end up doing. So method 2 kind of got us here. Method 1's a little tricky on a lot of cases. So method 1 for me doesn't work or isn't as easy to apply. So I'm kind of not necessarily using method 1 unless I've seen the molecule in an example like that's worked in the past. So method 1 to me is kind of hard to apply. Method 2 and 3 are my usual go-tos for Lewis structures. Now let's look how method 3 might be applied here. Carbon is our central atom. How do we know that? Well, it's just NCO. Like whenever you see 3 atoms given, like that's the arrangement of the atoms. Like if we had NOC or CNO, then this would be reverted. We would have the connection of the atoms in the actual order that they're given in the formula here. So C, then O, then N. So remember how we single bond first, complete octets by method 3 is that general rule. And then we look at the formal charge of carbons at 2+, so we can pull in, make a double bond, lose the lone pair here, drop the formal charge. Nitrogen actually started off before the double bond at -2, so now it's down to a minus formal charge. It currently would be 6 electrons surrounding the nitrogen, and then should have 5 for a 0 charge, so that's -1. Carbon now is a +1. With just the 2 bonds, it was +2, but now with the double bond on nitrogen, it's a +1. So we can get the formal charge of carbon to 0 by making another double bond. So CO2 structure would take one off the other atom, make a double bond over here. So if we do that, let's do a little cleaning. So let's erase the lone pairs. We now have 2 double bonds. Now what's wrong with this structure? Well, with this structure here, we have formal charges now of 0 on carbon, 0 on oxygen, but a minus on nitrogen. Okay, and so then we might say, okay, what else could we do? Is that the best Lewis structure? Well, we could have also had made the triple bond and left the oxygen as negative. So we could have made the triple bond, lone pair on nitrogen, single bond still to oxygen, negative formal charge is now on oxygen. Now another one that we could have done is said, well, what if we just put the triple bond to oxygen, single bond to nitrogen, -2 over here. Okay, so I have 3 possible Lewis structures. How do we judge which one's right? And a plus on oxygen. So 6 should be the electron count for oxygen. It only has 5 electrons surrounding it, +1. Nitrogen should have 5 electrons surrounding it for a 0 charge. It's surrounded by 2, 4, 6, 7 electrons for a -2. Okay, now the formal charges are maximized here. So that structure is obviously bad. -2 and plus are higher formal charges than either one of the other 2 compounds. So then when I'm judging, do I want the negative charge to reside on nitrogen or on oxygen? We want it on oxygen. So we want the formal charge to reside on the oxygen atom because it's the more electronegative atom, as opposed to the more negative charge on the lesser electronegative atom, nitrogen. Okay, so we can come up with 3 Lewis structures for NCO-, and we go with the Lewis structure that minimizes the formal charges and then puts the most negative charge on the more electronegative atom. So the formal charges between these 2 compounds are the same. They're as minimized as each other, but then we're putting more of the negative charge on the more electronegative atom. Now let's contrast this with CO2. So with CO2, this is, of course, our Lewis structure, but we could have considered, or the book kind of shows a couple considerations for a triple bond, single bond, minus, and a plus, and then also doing the same thing on the opposite oxygen, triple bond plus, single bond, minus, that these structures are disfavored because they're maximizing those charges. We don't want to maximize the formal charges, we want to minimize them when we're comparing Lewis structures where all else is equal, where we're satisfying the octet rule equally for the atoms in the molecule. So if we're satisfying the octet rule in all cases, then we're choosing the structure that minimizes the magnitudes of formal charge. So we had presented the strengths of bonds back in chapter 5. So you might remember seeing a chart like this before. So a CH bond 413, OH 463, FH, HF bond 567. So interestingly, you can see that the bonds are becoming stronger as the bond length is actually decreasing with that trend because F's a smaller atom than oxygen, also a smaller, oxygen smaller than carbon. And then also the electronegativity difference between the atoms is increasing. So as the bonds are becoming more polar, the bond strengths are going higher. So that as you have something like HF adopting partial negative, partial positive charges, you end up with a stronger bond, that this bond is strengthened due to the electrostatic attraction now that these charges have for each other. So you have an ordinary strength of bond for sharing the electrons, like, for example, a really weak nonpolar bond would be like an F2 bond. Where's F2? Over here. So two fluorine atoms has a relatively weak bond, 155 kJs per mole, because there's no charge being separated between the atoms. And if you adopt an HF molecule where you have some electrostatic attraction embedded into the atoms, then you strengthen that bond. Likewise, if you compare single versus double versus triple bonds, like carbon-carbon single to double to triple, you see the triple bond's a lot stronger, it takes a lot more energy to break a triple bond than a double bond. So if we're thinking about bonds, like we had shown a chart before of like hydrogen. So one of the ways to think of bonds, usually I think of zero as being the energy of the plateau, that you bring the atoms together, there's always some happy point where the molecule reaches a minimum energy. So if we're talking about H and H coming together to form H2, this is at about minus 436 kJs per mole. So that if we have an H2 molecule, it's going to take 436 kJs to break that bond. And then this optimal distance occurs at about 0.74 angstrom. So if we were to compare this to like a carbon-carbon single bond, like and say, well, what would a carbon-carbon single bond look like? Well, the two C atoms are a little bit bigger, so our bond length is going to be a little higher, and then the bond strength isn't quite as strong. So if you're bringing together two carbon atoms, then when they're infinitely separated, there's no energy. Then you start bringing them together, and the energy drops and not quite as low. And eventually it starts going up. Now the energy is going up in the region here and in the similar region for hydrogen here because you get nuclear repulsions. So this is due to the nuclei repelling each other because the nuclei, of course, are positively charged and like charges repel. So this is due to like charge repulsions. Okay, and so the carbon-carbon bond is a little bit longer than the hydrogen-hydrogen bond. Now think about the carbon-carbon, so that's a carbon-carbon single bond. Now think about how this would differ for forming a carbon-carbon double bond. So let's make a carbon-carbon double bond. Now the double bond is going to grow shorter and also stronger. So for the carbon-carbon double bond, what it's going to look like is it's going to be shorter than the single bond and then stronger. Okay, so the carbon-carbon single bond length is longer than the carbon-carbon double bond length, and we can I'm actually scrolling to a different chart on my computer so we can take a look at the difference in their bond length trends. So the carbon-carbon single bond length is 1.54 angstrom. And then the double bond length for the carbon-carbon bond is 1.34 angstrom. So the double bond is stronger, so it plateaus to a deeper energy. So the carbon-carbon double bond strength is 614, single bond's only 348. So this is comparing what separating two carbon-carbon bond lengths to form separated carbon atoms might look like. So if we're going to have a carbon-carbon double bond, and we want to separate those atoms back to two separated carbon atoms, that's going to take 614 kJs per mole, only 348 kJs for the carbon-carbon single bond. Okay, so hopefully that gives us a sense of the relative strengths of bonds and how whether or not we're comparing polar versus nonpolar bonds, or whether or not we're comparing double versus single bonds, how the trends correspond with those different types of bonds. Okay, so this slide here is comparing our bond lengths. So single to double to triple, the bond length is decreasing. So we've talked about that a lot already. Now triple bonds are shorter than double bonds, more electrons to hold the nuclei together. Fewer electrons, longer bond, fewest electrons, the longest bond. And the same trend is seen with CN bonds. Now notice nitrogen atom. Nitrogen's a little bit smaller than carbon because size decreases from left to right. And so the CN bond, notice how it's a little bit shorter than the carbon-carbon single bond. And then likewise, the carbon-nitrogen bond. Actually, it's a little bit longer than the carbon double bond, but the trend is still decreasing from where the carbon-nitrogen single bond began. Now, CO, single to double to triple, decreasing in length as we go from single to double to triple. And the same thing for nitrogen-nitrogen bonds, size is decreasing. So we can compare that our triple bonds are shorter than our double bonds, shorter than single in terms of length. But the strength trend is the opposite, that the triple bond is the strongest bond, stronger than the double, stronger than the single. Okay, so let's take a look at this question here. So using the bond enthalpy chart, can we estimate the enthalpy of reaction for the, the combustion reaction of ethane? What I wanted us to recall was that ethane C2H6, we're not going to see nomenclature on the next test, so I will probably update this slide for class tomorrow to say the combustion of C2H6. So what I want us to recall in this example is that hydrocarbons combust with oxygen to form CO2 and water. And so we're going to need, if we go 2 CO2s, 3 waters, we're going to have then a fraction of oxygen, so let's double C2H6. So now we need 4 CO2s, and then we'll need double, we'll need 6 waters. And so that's 3 oxygens plus 4, so that's 7 O2s. Okay, so using the bond enthalpy charts, we can estimate the delta H of this reaction by taking the sum of the bond strengths of the reactants bonds that we have to break minus the sum of the product bonds that we form. So this is the broken bonds, this is the formed bonds. The reason why this works is the bond strength for like O2 to 2 O's, 495 kJs per mole from the chart. So it takes 495 kJs to break a mole of oxygen bonds to 2 oxygens, so that takes energy. And then if we were to take, say, an O and an H and form back one OH bond, then we get energy back. So this would be minus 463. The bond strength of hydrogen is plus 463. So the bond strength here would be minus 463 kJs per mole of OH bonds that we're making. So making bonds is exothermic, breaking bonds is endothermic. Okay, so we're taking, and then we also need to know the structure here, of course. So C2H6 would be carbon-carbon hydrogens. Method 2 works really well. Carbon having 4 bonds, so no double bonds for carbon here. This is all single bonds. So we need 2 of these plus 7 oxygen-oxygen double bonds forms 4 carbon dioxide molecules plus 6 water molecules. Okay, so to approximate our delta H, what I need to do is count my bonds. So I have 1, 2, 3, 4, 5, 6 CH bonds times 2. So I have 12 CH bonds. The CH bonds are 413 kJs per mole. So 12 moles times 413 kJs per mole. So I'm just canceling the moles out without writing it. Save space. So I take 7 moles of oxygen times 495 kJs per mole. So So that'd be kJs, and then minus the sum of the products bonds. So I have 4 times 2, so I have 8 carbon-oxygen double bonds. That is 799. And then plus 12 times 463 kJs per mole for water, the bonds of water that we're making. And so if we do this arithmetic, then we would arrive at whatever the answer is. So it should be exothermic. It's a combustion reaction. So we would predict that this should be an exothermic reaction just from the nature of a combustion reaction. And so maybe we'll actually work on calculating that later. Okay, so let's move into chapter 9. Overview. We're going to talk about shapes of molecules, the difference between molecular polarity and bond polarity, and then some bonding models. So we've mentioned before that a Lewis structure does not necessarily tell you or show you the real shape of the molecule. And this is best exemplified with a molecule like CCl4. We draw a Lewis structure, 4 single bonds. That's what we hope to gain from the Lewis structures, that we get 4 bonds around a carbon atom, 2 chlorine atoms with lone pairs. Now the real structure of the molecule is going to depend on these bonds contain electrons, 2 each. Electrons repel each other. If the molecule really adopted this planar arrangement, then these bond angles would be 90 degrees. Those electron pairs would be much closer together than if the molecule adopted a 3-dimensional shape of, say, a tetrahedron. So if you have the CH4 with, or CCl4, I'm sorry, with a carbon-chlorine bond angle of about 109.5 degrees, say it's in the plane of your paper, your sheet, and you have one chlorine coming out at you and one going back away from you, the way we can draw this is with like wedges. So imagine you have a carbon-chlorine in the plane that we've written it, and then one of the chlorines coming out and one of the chlorines going back. All of these bond angles turn out to be exactly the same. So this bond angle for all of these angles is 109.5 degrees. Now that just turns out to be geometrically the bond angles for an atom right at the center of a tetrahedron. Now the tetrahedron is defined by this shape here. 4 quadrants or 4 points around a pyramid is the shape that takes the name tetrahedron. Now what this does is it spreads those electron pairs out. So the bonding pair electrons are now further away from each other and hence experiencing a lesser repulsion. Now CCl4, is this a polar or non-polar molecule? So let's review that a polar molecule would be something like HCl. So partial negative, partial positive, charge spread out across the molecule, polar bond, polar molecule in the case of HCl. So this would be an example of a polar molecule, and it has a polar bond. Now ClCl, chlorine, would be a nonpolar molecule for not having a difference in charge. So the partial charge is, or these charges are exactly 0, so no charge develops on the chlorine atoms in Cl2. So now what about CCl4? The carbon-chlorine bond is definitely polar. These chlorine atoms are certainly pulling electron density away from carbon, and they're all picking up a negative charge. So we get this ball of negative charge on the atom. Now, if I were to dangle a positive charge, so say I had a plus charge here, which of these negative charges would be attracted to the positive charge? Would the molecule move towards the charge? The answer is it would actually just spin relative to that charge. There would be no end of the molecule that would have an attraction and fly towards that charge. So there would be no net pull of the molecule. Whereas if you had something like an HCl molecule, the chlorine negative charge would sense that positive charge and then go towards it. So the negative charge here, you get negative charge around the whole molecule fighting for that positive charge, such that the molecule is not going to be able to move towards the charge. What we want to see for a molecule to be turned polar is one side of the molecule be a different charge than the other side. All sides of CCl4 are the exact same negative charge. So CCl4 ends up being a nonpolar molecule, despite having polar bonds. So it's nonpolar molecule, but with polar bonds. So it's not that the CCl4 bonds all of a sudden become nonpolar. They're still polar. The molecule still has negative charges. It's just you need one side of the molecule to have a different charge than the opposite side. Another way you can picture this, if you had two molecules of CCl4 like stacked on top of each other, would there be a net attraction or a net repulsion? So there'd actually be a repulsion because you'd have negative charge on negative charge. There'd be no way to arrange the molecule to have a negative on positive for a net attraction. So if we look at the shapes of methane, ammonia, and water, what we can make sense of in terms of their Lewis structures, of course, a similar type structure as CCl4 for methane. NH3 has the lone pair, and then water has two lone pairs. Okay, so the shapes of these molecules actually are all very similar in that all of these domains of electrons, so we have 4 total domains here, we have 4 total domains in the case of NH3, and domains just being pairs of electrons that are going to repel each other, and we get 4 domains with water. So all of these share 4 total domains. It's just whether we have 4 bonding domains versus 3 bonding domains versus 2 bonding domains. So CH4 takes that shape of a tetrahedral molecule. The lone pair of electrons would take one of the spots of a tetrahedron. When we think of the actual geometry name, we actually just name the geometry of the bonds, of the atoms. So we're going to look at just the atoms to come up with the name of the shape. The electrons are still there. The electrons are still determining the shape, so the shape of the overall electron domains is still taking the tetrahedral domain geometry, but the atoms, the geometry of just the bonds and the atoms, is a trigonal pyramid. So you get a pyramid of these atoms emerging because the molecule is non-planar. Now, planar versus non-planar is different than polar versus non-polar. Planar is just whether or not all the atoms in the molecule exist in one plane versus 2 planes or 3-dimensional shape. So ammonia, the nitrogen is in a different plane than the hydrogen atoms. So trigonal pyramidal, so you get a pyramid structure. Now water, anytime we have 3 atoms, it just becomes a question of, are the bonds linear? If it's linear, it'd be 180 degrees, but that's not the case for water. It ends up being bent in terms of its bond, closer to 109.5 degrees. Now, one of the things that ends up happening is these electron pairs of the lone pairs are actually closer to the nucleus because they don't have another nuclei pulling them further away. So because they're closer to the nucleus, they're actually going to send that bond angle to be a little less than 109.5, and the bond angle in ammonia to be a little less than 109.5 degrees. So the bond angle in ammonia ends up being about 107, bond angle in water about 104.5, simply because the lone pair electrons are exerting a greater repulsion. We'll take a look at that on another slide here in a minute. But are the molecules above polar or nonpolar? Well, CH4 is nonpolar. Now, the bonds aren't particularly polar in the molecule to begin with, but they're not situated in a way that they would make the molecule polar anyway. So CCl4 is nonpolar despite having polar bonds. Whether or not you classify this molecule as being polar or nonpolar, actually hydrogen's electronegativity is lower, so they would be going partial positive. If anything, but it'd be a very small positive charge because the separation of electronegativity is very small. But they'd still have the same positive charge on all ends of the molecule. So CH4 is a perfectly nonpolar molecule. The dipole moment of this molecule would be perfectly 0. CCl4 would also be perfectly 0. No net dipole for the molecule, despite having bonds with perhaps a very small dipole. NH3 is a polar molecule because we have nitrogen pulling electrons away from hydrogen. They're adopting a positive charge, partial positive on the hydrogens, and then the partial negative charge on that nitrogen as it's pulling electrons from the hydrogen towards itself. So we get a negative charge on top of the nitrogen, and then we get the positive charge on the bottom side. Just like with water, we get partial positive hydrogens and then a partial negative oxygen. So we get a positive charge on one side of the molecule, a negative charge on the opposite. So NH3 and water, these are polar. So polar molecules with polar bonds. So we can take a look at polarity differences between CO2. Now carbon dioxide is a linear molecule. We only have 2 domains. The furthest they can get away from each other is being perfectly 180 degrees relative to each other with a linear bond. So the molecular geometry of CO2 would be called linear. And so then the partial negative charges on the oxygen pulling electrons away from carbon, they get exactly the same negative charge. So the ends of the molecule here are exactly the same negative charge. So if we put a CO2 molecule beside itself, then we would have the exact same negative charge. And so then think of stacking a molecule directly on top of each other or directly beside itself. So if we put another CO2 over here, whoops, then we would have just straight repulsion. So we put another CO2 over here, straight repulsion, put another CO2 directly on top of each other, then you still get the direct repulsion, not attraction. So no built-in attraction. Now, you may be thinking, well, what if we stack the molecules in a funny way? Well, that doesn't lead there to be any great attraction in the molecule. We need the molecules to be aligned side by side or directly on top of each other in order to have that strong attraction. Because CO2 lacks that strong attraction, because the molecule has a dipole moment of 0, the molecules of CO2 end up being much more weakly attracted to each other, which is why CO2 would be a gas at room temperature. Water, on the other hand, has a dipole moment. It's a polar molecule. If we put a water molecule on top of itself, then you'd have this plus charge being attracted to this minus charge. And so water would have a much stronger attraction to itself, therefore requires a greater amount of energy in order to reach the gas phase. So it exists as a liquid to a higher temperature than something like CO2. So we look at the shapes of like CO2, linear, 2 domains, BF3, 3 bonding domains, no lone pairs on boron. So remember the Lewis structure of BF3, 3 bonding domains, CH4, 4 bonding domains. So if we have only 3 domains and we're perfectly 120 degrees in a planar molecule, all the atoms existing in the same plane. If we tried to kick boron out into a different plane of the fluorines, then we'd be putting the fluorine bonding pair electrons closer together. Then they'd be approaching that tetrahedral bond angle, putting them closer together. So the greater the bond angle, the lesser the repulsions. But when you have 3 domains, the best way that they can arrange themselves is at 120 degree bond angles. So the idea here is the valence shell electron pair repulsion theory, or that the valence shell electrons are repelling each other, hence they're getting as far away from each other as possible, and adopting the shapes dependent on the total number of domains about a central atom. And so then we'll see anything with 3 domains, whether it's bonding or non-bonding, will fit into the trigonal planar geometry. Whether we have 4 total domains, it'll fit into the electron domain geometry of tetrahedral. If we have 5 or 6 domains, 5 domains fits into trigonal pyramidal, so that'd be something like PF5. So PF5 would have 2 fluorines connected on an axis, another fluorine 90 degrees relative to those, and then the other fluorines on a trigonal plane with that central fluorine. So these are perfectly 120 degrees in the same plane as that phosphorus atom. So you get a trigonal plane connection here, 120 degree bond angles, axial plane, 90 degree bond angles. So this would be an axial position, and then these fluorines are said to be on the equator. So these are the equatorial fluorines. We'll see why that matters on the next slide or in a couple of moments. Octahedral, we have something like SF6 as an example of a molecule that has 6 bonding domains. So we'd have 4 atoms all on an axis, and then also 5 and 6 being on the exact same axis. So all of these are axial atoms. They're all on an axis with each other. So 3 FSFs all on the same axis as each other. So let's compare some bond angles. So we get perfect tetrahedral for ammonia, for methane, perfect tetrahedral, 109.5 degree bond angles all the way around the molecule. The ammonia, 107 degrees, because we get slightly greater than 109.5 degrees in terms of the lone pair hydrogen bond angle. So the lone pair is exerting a greater repulsion on the bonding pair electrons, decreasing that bond angle. Same thing with water, 2 lone pairs, exerting an even greater repulsion, decreasing that bond angle a little bit more. If we look at the case of like BF3 is perfectly 120 all the way around. CCl2 with a double bond to an O, this bonding pair of electrons are a little bit closer to the carbon atom because oxygen is a smaller atom than chlorine, and you now have 4 pairs of electrons in that bond. So those electron pairs are exerting a greater repulsion on the chlorines, setting that bond angle less than 120 degrees, down to about 111, and then the ClCO bond angle is slightly greater than 120. If we think about having the lone pair of electrons in something like SF4 would have 4 times 7 plus 6, that's 34 valence electrons. So when you do 32 electrons surrounding the Fs, then you end up with 2 extra electrons on sulfur. So that lone pair on sulfur is from these 2 extra electrons. Now they're going to be closer to the sulfur, pushing these bond angles slightly into each other and slightly decreasing this bond angle, so that this bond angle here would be about 174 degrees. So the electron pair bond angle to them is pushing it slightly greater than 180. So the FSF bond angle, not 180, but it's a little less than 180 degrees in terms of the bond angle of the atoms, relative to the electron pair a little bit greater. And then the FSF equatorial bond angle, a little less than 120 degrees due to the electron pair repulsions. So electron pairs repel bond pairs more than bond pairs repel each other is a conclusion that we can make from this slide. So we can give names of the geometry names, estimate bond angles, predict the polarity of these molecules like HCN. I get this applying that idea: 4 bonds to carbon, 3 to nitrogen, end up with the structure 0 formal charges all the way around. 1 plus 4 plus 5, 10 electrons to check, 2, 4, 6, 8, 10 electrons. So that checks out. But the bond angle here, 2 domains, perfectly 180 degrees is our prediction. We should have a partial negative nitrogen fighting for the triple bond electrons, carbons fighting off the hydrogen for electrons, so we're getting a different charge on this side of the molecule compared to this side. Now we don't necessarily need one side of the molecule to be plus and minus per se. We just need the charge on one side of the molecule to be a different charge than the opposite side. So this should definitely be a polar molecule. So we got a polar molecule, bond angle 180. Now this is a linear geometry, so the geometry name would be linear. Ozone, 3 atoms. Now 3 atoms, it's either linear or it's bent. So let's take a look at the Lewis structure. So 3 atoms of oxygen connected together. I kind of know it's bent, so I'm already going that way. But the way we get there is to do lone pairs on the oxygens. That would be 3 times 6 for 18 electrons. So we have 2 more left over. They go on the central oxygen. And so then we make a double bond because we have a big formal charge on oxygen. So we make a double bond. We could have the resonance with the other double bond. We have to stop here because oxygen's in the second row. We can't expand the octet of oxygen. So we end up with a positive central oxygen and then a minus oxygen in terms of the one with 3 lone pairs and a 0 formal charge in the opposite. Now, in terms of domains, it's pretty simple here. And in fact, we may just recall that the geometry should look like 2 equivalent bond lengths for the oxygens due to resonance. And so the 2 bond lengths should be exactly the same for the 2 O's. And the bond orders of those should be about the order of 3/2, a little bit longer than a double bond, a little bit shorter than a single bond between 2 oxygens. Okay, so in terms of chapter 9 here, the geometry name here, we have 1 domain, 2 domain, 3 domains. We have 3 total domains. So the electron domain geometry is trigonal planar, but the molecular geometry name here would be bent. So ozone, its geometry is bent. Now the bond angle here, electron pair repulsion is a little greater. We'd expect the bond angle to be a little less than 120 degrees. OF2, 6 plus 2 times 7 for a Lewis structure, 20 total electrons, central O, fluorines connected, lone pairs, that's 16 electrons, 2 left over, onto oxygen. So it looks just like water. Bent bond angle here should be less than 109.5 degrees. Close to 109, but a little less due to the electron pair repulsions being greater than the bonding pair repulsions. Now let's think about the polarity of ozone. So ozone has a positive charge up on top, negative charges on the oxygens below. So ozone would be best described as being a polar molecule. Now, you may look at O's and say, well, how can an atom or a molecule that has the exact same atoms end up being polar? Well, the answer is it's because the charge. We get a separation of charge. All polarity needs is a charge separation in the molecule. We have net charges on oxygen about minus 1/2. Minus 1 in one structure, 0 in the other, averaging out to minus 1/2 each. Positive charge up on top. All we need to create a dipole moment is a charge imbalance, a separation of charge. And so we get one charge on one side of the molecule, a different on the opposite, definitely a polar molecule. OF2, fluorine's more negative, partial negative, oxygen partial positive, so definitely a polar molecule in the case of OF2. Now what this means is we would expect our dipole moments not to be exactly 0 or close to 0. Polar molecules have non-zero dipole moments. Non-polar molecule, like Cl2, would have a dipole moment exactly of 0. CO2 would have a dipole moment exactly equal to 0. But polar molecules would have dipole moments greater than 0. Okay, give the molecular geometry name, bond angles here for these examples. SF4, we saw that on the previous page. We saw a picture of it, but we didn't go through like the name of the geometry. So this one here is fitting into the category of having 5 total domains. We did the Lewis structure already earlier. Let's actually go to this right here and say, why would this have necessarily been the Lewis structure? Like if we're thinking of a trigonal planar geometry, why this one and not this one? Do you see the difference? So the difference is I have the general shape of the trigonal pyramidal. So the trigonal bipyramidal looks like this. So it's, do I replace this pair, the axial, or do I replace an equatorial with electron pairs? And well, the answer is really decided by nature. You look at SF4, its real structure looks more closer like this structure here, and not like this structure here. So you can go to nature and see, well, what did nature choose? And then you could try to understand, well, why might nature have chosen that structure? What might make that one better than this one? Well, this structure here ends up with 3 90-degree interactions. So we end up with like 3 90-degree interactions with that lone pair. Here we only have 2. So the electron pair lone pair reactions are stronger than the bond pair interactions. So it might make sense that we want to reduce the electron pair bond pair interactions and have fewer 90-degree interactions. So you can understand a little bit why nature might have chosen this structure here. Now CLF3, let's actually finish the question. The question said, what's the molecular geometry name? Well, if you were to maybe draw this structure like this, then you can see that this looks kind of like a teeter-totter or a seesaw. So the molecular geometry name for this one, a little bit weird, but it's a seesaw. You're trying to describe the shape of the atoms in the molecule. So you're just trying to name the shape that the atoms take in the molecule. Now the electron domain geometry is still a trigonal bipyramidal. The shape of the molecule is still determined off the 5 total domains that the molecule has, but the shape, the molecular geometry name just takes the shape of the atoms in the molecule. And the polarity here, this should be polar. And so the molecule should be polar because we have negative charge on this side of the molecule and we have a positive charge on the sulfur end of the molecule. So there's no negative charge to counterbalance on the left side of the molecule, the negative charge here. Now if we had something like PF5, so if we had PF5, which looks much the same, but the only difference being instead of a lone pair, we have a fluorine atom. This would be a nonpolar molecule. So PF5 would be nonpolar because you have negative charge in all spots in the molecule. No end of the molecule is a different charge in the opposite end. Now the case of ClF3, 7 times 4 for 28 electrons. Make this a little smaller. So ClF3, we have Cl, F, and then F, and then lone pair. So lone pairs end up going 120 degrees relative to each other on the equator, and we end up with a T-shape emerging within the geometry. So if we were to rotate this structure, then we'd have a T-shape with electron pairs. It's kind of hard to draw these pairs, but coming out and into the page. So we get this like T-shaped geometry. So that's why this would be a T-shaped geometry for the name of ClF3. Polar molecule. Now the bond angles here, we predicted these earlier for SF4 in an earlier slide, less than about 120 degrees, less than about 180 for the FSF angle. Now the same thing here. This angle here should be less than 180 degrees. And like the prediction here isn't to put an actual number, but to say it shouldn't be exactly 180, but it should be close to it, but a little bit less than 180. Bond angles here should be perfectly 90 if it were a perfect T-shape, but it should be a little less than 90 degrees due to the electron pair repulsions, with those bond pairs being greater. Xenon F2, 8 valence electrons for xenon, plus 2 times 7. Xenon does pair up with fluorine at low temperatures. Not a real stable molecule. You're not going to put this in a container and ship it around the country or anything. But you get 22 total electrons, central xenon, fluorines attached, lone pairs. And then that's 16 electrons, so then we have those electrons left to go. And so the way this would work is, this might be easiest seen if we draw this vertical. So we have a xenon, fluorine, fluorine, and then lone pair, and then lone pair on the trigonal bipyramidal geometry. So now we have electron pairs pressing exactly on both sides of the xenon F xenon, so that our bond angle results at being perfectly 180 degrees. So you have electron pairs forcing both of these angles exactly around the molecule. So again, perfectly 180 degree bond angles. Perfectly non-planar, or non-polar for the polarity of this molecule. So non-polar molecule for xenon F2, but polar molecules for ClF3 and SF4. Non-polar if we had all 5 bonding domains in trigonal bipyramidal domain. So non-polar for PF5. So this page here contains molecules that will have 6 total domains. So 6 domains, if they're all bonding, will look like something like SF6. So SF6, octahedral geometry. Now the name octahedral actually comes from this shape here. We get 4-sided pyramid on top and in the bottom. So the 8-sided shape you get here is where you get the name of octa for 8 and hedral. So you get that octahedron shape for the outer atoms on this molecule. So still only 6 fluorines, but octa doesn't have to do with the number of fluorines attached to sulfur, but the number of sides of the shape of the pyramid that emerges from this structure. So SF6, partial negatives balancing each other out across the molecule. All these dipoles are oriented in such a way that they cancel out. Net dipole moment of 0 for SF6 for a nonpolar molecule. Now BRF5, very similar. 7 times 6, 42 electrons. So that's bromine with fluorine's opposite. And then 1 extra pair of electrons. So each of these fluorines would have 8 electrons each. That's 40 electrons, so 2 electrons left over onto the central atom. So that electron pair is going to cause these bond angles to be a little less than 90 degrees, and then the internal F bond angles here to be a little bit less than 180 degrees. Now we are going to end up with a positive charge on top of the molecule, negative charges beneath it on the sides, so we end up with a polar molecule. So we need all those bonds to be exactly opposing each other in order for the molecule to be nonpolar. So xenon F4, 8 plus 4 times 7, that's 36 electrons. So that's going to be xenon with, let's think of the best way to draw this. Let's do fluorine, 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 and then a lone pair going back, a lone pair coming straight out. The lone pair is pressing above and below on the fluorine, so their bonding will stay exactly 90 degrees, not less than 190, but exactly 90 here. And the molecule has the fluorines exactly opposing each other, so that the molecule has no net dipole moment. Exactly 0 for the dipole moment, non-polar molecule. Okay, so we can predict molecular polarity from knowing the structure. Now we'll see in chapter 11 in more detail, but polar molecules will be more attracted to themselves and have a generally higher boiling points and melting points than compounds without those types of melting points. Something a bit of an aside, but there's a compound like tungsten hexafluoride. Tungsten's molecular weight's like over 200 atomic mass units. Usually molecular weights go up with, usually boiling points and melting points go up with size. This molecule is actually a gas at room temperature. It's actually the biggest known compound that's still a gas at room temperature because there's no net dipole moment in the molecule is one of the reasons why. So polarity is a pretty important concept that we come back to later in the class. It's a really important concept as you get into organic chemistry as well. We can also apply VSEPR to multiple central atoms. Like we sometimes draw these flat Lewis structures because it's easy to do, like CH3, C double bond O to H. Then we can easily look here and say, well, that should be a tetrahedral CH3, this should be a trigonal planar, and this should be a bent bond. So we can sort of very easily be able to say, okay, like we can interpret the structure in such a way that we get a hydrogen, a carbon, hydrogen coming out, hydrogen going back, carbon, double bond, oxygen, oxygen, two hydrogen with lone pairs. So you can sketch these like three-dimensional shapes pretty easily, get bond angles to be about 120 degrees here, even slightly less due to the double bond repulsions probably being a little greater. These bonding angles here are probably close to 109.5, pretty close to exactly, and this should be probably a little bit less than 109.5 degrees. And so tetrahedral for the first carbon, trigonal planar for the second, close to 120, tetrahedral for the second for this one here, and maybe even predicting slightly less than 109, slightly less than 120 if you're talking the carbon to oxygen bond angle due to the double bond repulsion. So you can even come up with a little bit of a prediction if they should be exactly dead on or really close to those bond angles, or maybe slightly less due to our understandings of some of these repulsions. So we have this molecule here. For the oxygen here, this would be a bent bond. We have 4 total domains there. For the next atom, we have 1, 2, 3 domains. The double bond still counts as one domain. And so then the predicted bond angle for the for the HOC, that will be determined by the bent bond off tetrahedral, close to 109.5 degrees. The bond angles here would be closer to 120 because that's trigonal planar. So this would be a trigonal planar geometry, close to 120 degrees. Let's not worry about greater than or less than here. It's a little bit more complicated. Really, we're just trying to see more simply in the structure. 3 domains are on the second carbon in the molecule. So trigonal planar here as well. So the bond angle is about this carbon here, would be close to 120 degrees. So it's like common on a test to give like something like this and say, well, what are the bond angles here? And a lot of people go with 90 degrees because it looks 90 degrees, but you have to interpret the Lewis structure as not the real molecular shape, but use that to help you understand, 4 domains should be tetrahedral, so these are truly closer to 109.5 degrees in a real molecule. So molecular shape and polarity summary, BF3, nonpolar, all those bond dipoles oppose each other. We have a trigonal planar structure, negative charge, all ends of the molecule, so nonpolar. HCl is polar for sure. We have a polar bond and hence a polar molecule. We need a positive charge on one side or a different charge on one side of the molecule compared to the opposite. CH3Cl is a pretty interesting case where we have a partial negative up here, different charges below, so polar molecule. CH2Cl2 is a good example too. So if you go to this molecule here, this is dichloromethane. So dichloromethane, you draw it like this, you may say, these dipoles are opposite. This molecule should have a dipole moment of 0, but that's wrong. It's wrong because that's not the true structure. That bond angle is actually 109.5 degrees. The real structure would look like carbon, chlorine, chlorine, hydrogen, hydrogen. So we get partial negative, dipole pointing this way in the molecule. So we get a partial negative charge over here, partial positive on the opposite side. Definitely a polar molecule. NH3 is polar, CCl4 though is nonpolar. So covalent bonding and overlap. So one of the models of bonding is valence bond theory, which says that when orbitals can overlap, then you can get bonds that result. So you take the largest orbital of an atom and then see if you get overlap with some other orbitals, like a 1s can overlap with a 3p, or the two 3Ps, the two chlorines can overlap to make a bond. So generally the greater the overlap, the stronger the bond. So the greater the overlap, the stronger the bond. So you bring atoms together, you get this orbital overlap, and then you can't continue to increase again due to like charge repulsions. So the nuclei repel and the two electrons repel, kicking the energy upward beyond some optimal bond distance, about 0.74 angstrom for an H2 bond. Chlorine-chlorine bond, probably a little longer because the chlorine atoms are bigger. Now, if we want to see something like beryllium difluoride and the types of orbitals that might be involved here, what we might want to do is adapt a model so we can get overlap. So if we take an S, we look at beryllium and say, what if it uses its 2s and one of its 2p orbitals? And so allow these to mix together. You get two hybrid orbitals. They look like two big p orbitals pointing in either direction of the beryllium. So this is just so you can get overlap. So you can see how you might get overlap with the fluorine atoms. So you can use valence bond theory to try to come up with hybrid orbitals to get overlap for molecules. So if you allow beryllium to be what we call an sp hybrid, so take one of its s orbitals, one of its p, mix them together, and then get two different orbitals, they point together in 120-degree bond angles. Now this isn't really geometry class or anything. This is just a simple idea of if I need to get two bonds on either side, I need two orbitals. So I take two orbitals, mix them together just into the right shape that I know I need for 180-degree bond angle for a linear molecule. So I know this should be a linear molecule to begin with, so I just come up with like linear orbitals with this hybrid orbital approach. So it's coming up with like what the orbitals might look like in beryllium difluoride in order to get overlap that we might expect applying valence bond theory. Okay, so if I'm trying to get overlap for bonding in something like BF3, the first thing I might recognize is that if I'm picturing my three p orbitals, I have a px, a py, and a pz. None of those are at 120-degree bond angles. So how am I going to get overlap with the fluorine atoms at 120-degree bond angles? Well, what if I just magically take an s and then two p's? So I have three orbitals that need to be made to make this molecule. So I take three orbitals on boron, mix them together. So take a 2s and then say a 2px and a 2py. And then leave behind the 2pz. So the 2pz orbital is unused. So I just leave that one behind. So I take the s, the p, the other p, and just mix them together and then come up with three new orbitals pointing in the 120-degree angle positions. Now, again, this isn't geometry class. You don't really mix this shape, and this shape and get the three orbitals resulting in those directions, but you're just coming up with a model that if you did get orbitals averaging out or mixing together in this process, then you could get overlap. We can take fluorine orbital and then overlap it and get that overlapping orbital with a 2p of fluorine to get bonding overlap in order to make the bond. So this idea here is just saying, well, if we believe orbitals come from the bonding orbitals come from the overlapping of atomic orbitals, and then boron doesn't have an atomic orbital naturally where we need one to be, then let's just mix the orbitals together and make one where it should be in order to get the overlapping where we know from the structure of the molecule that the atoms actually reside. So if we need 120-degree bond angles, let's just make orbitals with 120-degree bond angles, and we call these hybrids. So this would be an sp2 hybrid orbital. So taking two p orbitals and an s to make this hybrid set of orbitals. And so lastly, we have the hybrid orbital set to make the bonds in something like CCl4. So again, we don't have any atomic orbitals on carbon naturally at 109.5-degree bond angles. So why don't we take all four of the available orbitals? We have the 2s, the 2px, the 2py, and the 2pz orbitals available for carbon. That's its valence shell, all of its orbitals. And we know it's going to fill all of those orbitals because it ends up with 8 total electrons surrounding it. So we take all of its available orbitals. So we take an s and then 3 p's for an sp3 hybrid set. So we take a 2s, 2px, 2py, 2pz, and mix these orbitals together and get 4 new orbitals pointing in 109.5-degree bond angles relative to each other. So we then end up with orbitals exactly where we need them to overlap with p orbitals, or whatever the orbital is, on our atom that's attaching to those spots. So it's just the idea, hybrid orbitals are just giving us orbitals to allow there to be overlap between the now hybrid orbital set on our central atoms with the atoms surrounding them. So now if you look back at something like Be beryllium difluoride with the sp hybrid set and Bf3 with the sp2 hybrid set, so sp here, sp2 here, that you have two leftover p orbitals. So on beryllium, you have one leftover p orbital, and then you have a second leftover p orbital that are not being used. So these are like unused p orbitals. You used one of the p orbitals to make this hybrid orbital here. So you used one of the p orbitals already, and the other two are unused. And BeF2, it's like we're using these two to hybridize, and then we have the unused orbital sticking straight out of boron. So we have one leftover p orbital. So we have the leftover p that's unhybridized, and we have the p plus p that are unhybridized left over in BeF2. What we're going to see later on is that those unused p orbitals are what can be used to make double bonds or multiple bonds, so that the unused orbitals can then overlap with other unused p orbitals to make multiple bonds. We'll talk about that later. All right, that's all for this video. We're going to basically see this content lecture again tomorrow, so if you're watching this, hopefully this gives you a bit of a better idea of what to expect tomorrow, and hopefully you can get a little, get the most out of lecture having watched the video. So thank you for the attention. We'll see you in class.